Good afternoon, everyone. My name is Liu, and I'm the rising third-year PhD student in the Department of Industrial Engineering. And today, I want to talk to you about the size. To start, this is a small piece of image, and I want to guess what is the object in it. It's a little hard to see, right? At least from my point of view. So, what about this one? It gives you some information about texture, but still very hard to recognize. This is probably the same situation as the second one, but this, it tells you it's a cucumber. So all these four small pieces of images are extracted from this large cucumber image. And here comes the question. What is the difference between these two that make you recognize the object is cucumber in one but cannot in the other? It's the size. So why a good size is so important? If you consider the left small piece of image gives you two localized information such that you cannot generalize to any object in your knowledge base. But this right one, it gives you the information of the shape, of the signature colors, and of its texture. And all this combined information make you make the decision, I'm seeing a cucumber. So long story in short, a good size in an image can give you the representative information to this object. And this cucumber example is actually connected to a concept named RVE in mechanical engineering. So RVE is the acronym for the representative volume element. And it is the smallest element of a microstructure such that it preserves the representative properties of the samples. It is very important because it's the basic element in the scientific study in mechanical engineering. I'm showing you an example of a drone. And let's say if we are interested in the damage performance of an LB in this drone, and we want to build a complex multi-scale model. And then we will break this L-beam from the macro scale to the meso scale, and finally to the micro scale. And we're going to build layer by layer. And all the properties you are going to drag in for this micro scale is coming from the properties you will study from the RVE. And that is why RVE is so important. And not only RVE is important, the size of RVE is also important. Why? Because it affects your simulation time. So in the left image, I'm showing you a 2 micrometer stationary microstructure, and to give you some clue, 2 micrometer is almost the thickness of a spider web strand. So it is so small such that you can see the small particles, which are the white pixels in this image. If we are interested in the strengths, such as the Young's modulus of this 2 micrometer stationary microstructure, and we run the simulation program on it, it will take you about 1.5 hours. But on the right, this image is an RVE of the 2 micrometer stationary microstructure. It's 1/16 of this one. But if you run your simulation program on it, it will take around 5 to 10 minutes. So long story in short, this RVE can cut your simulation time by a factor of 90%, but it still gives you the properties you are interested in. And now you would think, if the size of RVE is so important, there must be some existing method in the industry to find the RVE size. And the answer is yes. So currently, the standard method in mechanical engineering to decide the RVE is based on simulations. Let's say we have 3 candidates for the RVE size, 1, 2, 3. What we would do is, for each size, we are going to extract 3 samples. 3 for size 1, for 2, and same for 3. And then we are going to simulate on all these samples, get their properties, and draw their properties against the size. You can imagine there is a convergent constraint of this plot. And once this convergence is happening, we're going to stop this process and say, hey, hi, this is the RVE size we're targeting for. It's a very straightforward method, but it has an obvious disadvantage because I'm only listing three candidates here. And for each size, I'm only giving you 3 samples. In practice, if you want to get a good plot, you're going to have many more sizes and many more samples for each size. So that being said, you're going to need to simulate a lot of times, and this process is time-consuming. So here comes my research. We want to come an alternative to this current standard method that is based on simulations. So what we're going to do is, instead of measuring the variation of the simulated properties, we are going to consider what is the variation of these samples themselves. And then we can decide the RVE size. And this method is actually simulation-free. And we're going to do it by the help of machine learning and statistics.